All right, good morning. Let's see, question in chat, are we supposed to have comments in our make file? No, you don't need comments in your make file. You can put them in if you like. But I do want comments in all of your .c files, and go ahead and put them in your .h file if you're making a .h file also. Let's see, so quick question. Is it okay for our main program in PA1 to accept a character and then an integer with no space in between? That's perfectly fine. I'm not going to be super picky about error checking, other than, right, if you put in an illegal command, I want you to call that as an error. If you're supposed to say I followed by an integer and you don't put in an integer, I want you to call that as an error. I'm not going to get picky if you say I5 without a space in between. I'm not even going to worry if you say I space 5 space haha. But so you can ignore extraneous input too if you like. But definitely if I just say I, which I will, don't just insert some random number, right? If I just say I and I don't put an integer after it, say that's an error and don't do the insert. How strict will you be on makefile structure? I want a clean makefile, so if you have multiple files, right, you should compile just the files that change. So compile your .c's to .o's, link your .o's into an executable, throw in a make clean option so that I can like get rid of all the compile stuff and rebuild it myself. I'm not worried about structure beyond that. Looks like there's better and more complex ways to construct the makefile than what we learned in 224. If you want to do something fancier, that's fine, but there's no need as far as assignment requirements. Basically just, compile .c's to objects, link objects together, put in a clean option, and you're good to go. Our program doesn't have to accept extra input, does it? What sort of extra input? I mean, it doesn't have to accept that because that's not a valid command. But if you say I234 haha and you just want to say that's just inserting 234, I'm okay with that. Right, because I didn't specify in the assignment to catch that as an error. But it's straightforward to catch after 224, right? Just put that extra %s after your %d and pick up the extra stuff. Yeah, so if you catch that, that's fine. That's bonus stuff. How do we test the out of space error? Or how do we add 99 nodes without typing them all out? Good question. Write yourself write yourself a file that says insert 99 different numbers, right? And just copy and paste that in, and that should work. If you say X haha and it still exits, that's fine. So I'm not going to be picky about extra input on the line. All right, good clarifications. I'm trying new things. All right. What if it it inserts even if we do I space 24 with more than one space. That's fine. Basically, if scanf likes it, I like it. That's kind of a general rule. So multiple spaces are basically, you know, indicating separation between two things. Just like in Bash, you could say vi space, 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 name a file, and it doesn't create a file with a bunch of spaces in the beginning of the name, right? It just takes multiple spaces as a separator. So you're welcome to do the same thing. And if I like it, you like it. Cool. If I like it, your grade likes it. All right, good. Other questions? All right, let's start going through some more pseudocode. Let's finish up PA1. And PA1, remember, was originally due tomorrow morning. I've extended that until Saturday at noon, so you have a little bit of extra time. But let's finish basically going through the last details of PA1. So let's look at a search function. And what should we call our linked list today? I'm going to keep calling it LL. And I'm going to search for some number. And our basic picture, right, there's a sentinel. And each sentinel points to another node. Until it points to a node that says the next node is my null. Right, so that's how we know we're at the end. And so our basic search method is going to be, we want to begin with the first node and see if that matches our number. If it does, we're done. If not, we want to move to the next node and see if that node's data matches our number. And if not, go on and so on. So as usual, I'll have a current variable, right, an integer, to point to the node we're working with. And yes, you can call the main program anything you like, but don't call it something that's really hard for me to type, like, you know, supercalifragilistic or something like that, because I'll just rename it. All right, we'll have a current node, and our main loop is going to be something like if ll bracket current dot data equals num, then return, you know, a 1. I'm just going to say true because it's pseudocode. But, you know, if the current node's data matches our number, we're done. We found the number that you're looking for. Otherwise, we want to change current to be this next node. Well, where is the next node? It's ll current. That's the struct node we just looked at. And if we look at the next field, that's the index of the next node. So if we set current equal to that, that'll move us to the next node. And we're going to throw this whole thing in a loop. Awesome name for a linked list program, exactly. I'm impressed you could spell that. All right, so loop, two things to worry about, right? How do we initialize? When do we exit? So the exit condition is the same as when we were printing, right? When we get down to where current is our last node, we still want to do this check, right? We don't want to exit as soon as we move current to here. Once current points to this, this is still a node that we need to check. So if current is equal to data, we can say it's true. Otherwise, we will move current to, you know, the thing this points to, and now current will be my null. And now we want to exit. We don't want to We don't want to go on to anything else. So that's a perfect while condition, while current is not equal to my null. And that also tells us what we should do to initialize, right? Ideally, we'd like current to start off as our first node. So current equals the thing the sentinel points to. And then edge case check, if we have an empty list, what will this do? Well, if our list is empty, this will initialize current to my null. We'll kick out of the while loop immediately. And then just remember, if you come out of this loop, then it's not found. All right, do we need to print anything if there's nothing in the list, like a message? You want to print an empty line, and that's all. So you print basically, you know, a line containing nothing. That's the collection of nodes. All right, so that's your search setup. It's almost exactly like the print method that we put together yesterday, except instead of printing, we're comparing the data to our number. And if we find the number we want, we return right away. Now you can get fancier. Since we know the data is sorted, we could you know, check to see if the data node's value is smaller than the number we're looking for. And if it is, we know that we're done. We don't have the number. But, you know, keep it simple if you like. Just search every node. And it's the same order of complexity. All right, so delete and add are the ones that get more involved, because to delete a node or to add a node, we need to deal with the node that comes right before it. So let's draw our picture. And I'm going to put particular values in. So let's say this points to a 10. And this points to a 20. And this points to a 30, and this is null. For the init function, do we initialize the next value or only data and valid? The only thing you need to initialize in the init function is the valid flag should be 0 for nodes 1 through 99, and the next flag should be 0 for index 0, the sentinel. And that's all you have to do. But it's nice to initialize the data value sometimes so that if you stumble across a node that you haven't done anything with, you'll recognize it, right? So you could make them all some particular value, your zip code or something, and then they'll stand out if you bump into them. And yeah, if you want to do the data in next fields, that's fine. All right, so let's do delete first. Let's say we want to delete the 20. And we'll deal with edge cases next. All right. We're going to start at the sentinel. We're going to do the same drill that we did when we were searching. Man, my computer is just like weird. All right. We're going to do the same drill that we did when we were searching. We're going to start at the sentinel. We're going to move following the links. But we're going to do something different when we get to the node that we're looking for. Keep in mind all of your functions that you're writing that you call directly from main. So add, most all the functions, add, search, delete, print, right? All of these should work by treating the linked list as a linked list. Okay. So what do I mean by that? If you want to search for a node, you know, you technically could do it by making a loop from 1 through 99 and going through your array and checking to see if the data value matches and if valid is set equal to 1. You won't get points for that. Okay? You've got to do your search by starting with the Sentinel node and following the nodes moving forward. You got to treat it like a linked list. You could delete by going into your array and looking for, you know, an entry that has the data value that you want, and then setting the valid flag to 0 and finding the thing that has a next field that points to it and so on. Don't do that, right? You could print by going through, finding all the entries that have a valid field of 1, throwing those into an array and doing a bubble sort. Okay, you don't get points for any of those things. You got to be treating this as a linked list. The shortcuts might save you a little bit of programming time, but the goal here is to learn the data structure so that in PA2, when we start dealing with mallocs and pointers and all of this kind of stuff, we're not also trying to figure out what a linked list is, right? We'll have spent a number of days working with linked lists, and we'll understand that data structure, you know, well enough. So so to delete, right, as with all things, we're going to start at the Sentinel. We're going to follow the chain of links until we either get to the node that we want or we run out. Now, I've suggested in the write-up that you only call delete if you know that the node exists. So let me pull up the spec here, because there was a question about this. Right, you should only call this function if the number is contained in the list. So delete is a void. Okay, it does not return a value, because as long as you call delete only on numbers that are in the list, delete cannot fail. Right? It can't run out of memory. It can't fail to find the node, and it can't, you know, fail in its effort to delete the node from the list, unless something has gone wrong and a stray, you know, high energy particle has hit the memory of your machine and flipped a bit somewhere. Delete is like print, doesn't have to return a value, right? But this business of trying to delete something that's already in the list, that's handled by your main program. Okay, so the main program, if you say delete, have your main program see if the number's in the list. If it's not, say node not found. Otherwise, call delete and say success. All right, so we're going to start at the Sentinel. We're going to move forward. We're going to move forward. When we get down here, right, we're going to use this current variable to keep track of the node that we're on. So when we get here, we're going to see, hey, the current node's value is what we're trying to delete. The trick is we need to know what the previous node was. So we need to keep track of a pair of pointers and move them together. And then when we find we want to delete the current node, it's the previous node's next field that we update. All right, so how can we do this? And this will work for add as well as delete. The first node we want to work with is the thing the Sentinel points to. So we're going to start off with current right here. By symmetry, we might think, you know, the previous node should be the Sentinel, even though it's not part of the list. And this will actually work. This is why the Sentinel is there, so that we cannot have, we don't have to write a special case for when we want to deal with something at the beginning of the list. We simply set the previous node to be the same as the Sentinel, right? And this is going to work great, because if we decide we want to delete the 10, what do we have to update? We have to update the Sentinels next to point to, you know, the thing that came after 10. While having this previous point to the Sentinel is going to make that happen. So you want to seed your loop like that. And now it's pretty straightforward. If current, and I'm going to take advantage of the fact that I said this was pseudocoding and say if current.data, but I really mean LL bracket current.data, right? If the current node's data is equal to the number, then we want to delete the current node. So how do we delete the current node? Take the previous node and have it point where the current node is currently pointing. So if we're up here and we want to delete the 20, have the previous node point to wherever the current node points. And then return. So yeah, your search there's a question in chat. Search function should go through the linked list. Start at the Sentinel node, move forward until you find the node. If you run out of nodes, then it's not in the list. I'm looking to see how explicitly I spelled that out here. Yeah, so that's what this this business over here is talking about. So this was this whole abstract data type notion, right? So search, for example, searches for a node containing the given number. The above routines represent the interface between a main program and the linked list as an abstract data type, right? Meaning that those routines do not tinker around with the internals of how you're representing the list. Okay, to add a number, create a new node, search the list for the proper point to insert the node, adjust the prior node's next field, and adjust the new node's next field accordingly. Similar actions are taken for printing, searching, and deleting as discussed in class. Okay, so we're discussing it in class here. Yeah, so search by beginning with the Sentinel node, take the thing it points to, move until you either find your number or run out of space. Delete by doing the same thing, add by doing the same thing. Again, the reason for this is because in PA2 we're not going to have an array of struct nodes. The nodes are going to be stored somewhere in the 16 gigabytes of memory that your PC has, and you don't want to do a search on all of that to try to find your number in your list. So we're going to make our transition to PA2 easy by doing this. All right, so if the current node's data is equal to our number, that's the node we want to delete. So take the previous node and change its next value to be what the current node's next value is. And we're done. We can return at that point. Otherwise, move down the list. So previous equals current, and current equals current next. And go back up. That's our basic loop structure. That's our initialization. What's the exit condition? So give me some ideas in chat. How do we decide it's time to exit? I mean, we shouldn't run into a case where the node's not found, but where would that case be? So we got 3 answers so far. So if you run out of memory, we're not allocating anything here, so memory's not going to be an issue. We've got a current not my null, and we've got a current next not my null. And those are usually the two main ones that I see from people. Some people will put a check inside the code and do a return inside a forever loop. So let's break out the possibilities. Suppose, and this is not going to happen because your delete's only going to be called on a number that's in your list. But suppose you're trying to delete 40. Okay, we're going to move current down to here. That's not going to get deleted. We're going to move current down to here, and that's not going to be what we want to delete. When we move down the list, it's going to change previous to here, and it's going to change current to my null. So if we test for a condition at the top of our loop, it's probably current equal to my null. So I could do this as well. Current is not equal to my null. Now there's other ways we could do that, right? We could check inside here, right, at the bottom of our loop, and we could say, you know, right here we could say if current next is my null, then let's exit. But the problem with that is if there's nothing in our list, current is going to start off at my null, and we're going to end, if we do this as a forever list, we're going to do this check once before we get down to our test to see if current next is my null. Right, so that's going to hamper our empty list case. And we could do previous dot next. We could do, well, previous dot next is not my null. That doesn't seem as intuitive to me. But that's the one that seems kind of canonical to me. There's different ways to do it. But make sure that whatever you write is making sense to you in terms of your pictures. All right, so this should work if we're deleting the first node, right? In the case of deleting a 10, right? Current is that first node. Previous is the sentinel. Current is not my null, right? If current data equals num, what's it going to do? It's going to take previous next, that's the sentinel's next, and set it equal to current's next. So that's going to take this arrow and change it to look like that. So that seems good. And if we're deleting the last node, if we come down here to where this is current and this is previous, and we're deleting a 30, if it matches, it's going to take previous next and set it equal to current next. So previous next is going to get set to this thing's next, which is my null. And so it's going to basically change this prior node to be the last node of the list, which is, again, the correct thing we want to have happen. So you can usually special case your way out of issues, but sometimes you can write your code and you find you don't have any special cases, and that's usually a comfortable feeling that you're doing something in the right direction. All right, what's the one thing I'm missing from here? There's one function call I still need for PA1. I need something right in here. Change valid, right? So I'm deleting this current node. I need to mark the valid flag to 0 to say this node is no longer in use, so that some other time when I say get node, it can reclaim that. All right, how do I set the valid flag to 0 in PA1? Call release node, thank you. Made my day. So down here I'm going to say release node. Pass it the linked list, and I pass it the index of the node I want to release from memory. That's going to be current. And there you go. You can use release node in your init function, by the way. Right, your init function could loop from 1 through 99 and just release each of those nodes by calling release node. You don't have to do that. You can set the valid flag directly inside init. All right, questions on that? All right, so that brings us to the add function. We did print yesterday in actual code. We've talked about search. We did delete. Let's talk about add. And add is only slightly trickier than delete. But we need to be careful with edge cases. So let's add a 15. That's a nice number in the middle. And then we'll deal with edges later. So we're going to do the same pair of pointers, right? So the previous node is going to be the sentinel. The current is going to be I'll just say previous.next, but you know LL bracket 0.next. So previous current. And instead of searching for the number, we want to find the spot to insert. So search for first number bigger than n. So I'm just going to call the number I'm inserting n. So search for the first number that's bigger than n. So we're inserting a 15. Current node has a 10 that's not bigger. So we're going to move previous and current. Current node is 20. 20 is bigger than 15. Okay. At that point, we want to insert before that current node. So let's make a loop. So we've initialized previous and current. If current data is bigger than n, insert before the current node. If it's not, then move down the list. So set previous equal to current, set current equal to current, dot next, and go back up. And we'll deal with edge cases next. Okay, but what do we want to do when we find the spot where we want to insert? We want to insert before our current node. So what should we do? Well, let's before we do all of this, let's make a new node. So let's call getNode. And do your checks. If new is equal to my null, then return an error condition, right? Otherwise, new is the node we're going to insert into the list. And let's set its data value equal to n. Alright, so that's up in the top outside our loop. And then seed our previous and current so we can start marching through the list. And now we go into our loop and we move down until we find a current node whose value is bigger than our previous, bigger than the number we're trying to insert. Okay, so now we're at this case. We're inserting a 15. Our previous node is here. Our current node is here. What are the two lines of code that squeeze this new node into our list? So give me some code or pseudocode. Previous next equals new. I like that. So our previous node is no longer going to point to the 20. It's going to point to the 15. That looks promising. And then someone said new.next equals current. So take this next field, point to the current node, which is a 20. And we are done. So this is hopefully starting to make more sense, right? And if you just try to kind of in a vacuum figure out what these statements should be, it's going to be really confusing, and it's going to leave you feeling like you don't understand linked lists, right? Always start with, you know, some kind of representation of what you're trying to do, and, you know, hopefully you understand linked lists to say this should point to the 15 should point to the 20. Look at the variables and their current values at this point, right? This is new, this is previous, this is current, and then let that write the code for you for how to make that happen. Right? Yeah, exactly. Once you can visualize it, right, you're totally solid. All right, so that's the action part of our add routine, right, that actually does the insert. There are edge cases to deal with here, though. So the first potential edge case is what happens if we're inserting in the beginning of the list. Let's say we wanted to add a 5. And let me start a fresh picture here, actually. So here's our sentinel. That points to a 10. That points to a 20, and so on. And we're trying to add a 5. So we've got a new node with a 5. Well, when we seed our process, right, when we initialize things before the loop, previous is our sentinel, and current is the thing that previous points to. It's our first node. And the first time through our loop, we're going to say if current data is bigger than n. Well, in this case, current data is 10. That's bigger than 5. So we're going to want to insert right before here. Well, what were the two lines of code we just got? Previous next is new, new next is current. What's that going to do in this case? It's going to take the previous node and point that to new. And then it's going to take new and point that to current. And that's exactly correct. That works great. Because now the sentinel points to our 5, the 5 points to the rest of the list. All right, so inserting in the beginning is not an edge case. That's because we have a sentinel node. So back to our loop, we've got our initialization, we've got the body of our loop. What's the exit condition? Well, the exit condition is going to happen when we run out of nodes. That's usually the issue. And so if we just checked our current node, right, and that was not bigger than n, so say we're adding 3,000, or maybe 50. So we're adding something that hangs off the end of our list. How do we know that we're done? Well, when we move down the list, we're going to change previous to here, and current is going to be what that last node we checked points to, which is my null. And so once again, we can do this while my null is not equal to current. All right, so if we get to the end of the list, if we're adding a 50, previous was 20, current was 30, wasn't the right place to insert, we move down, now previous is 30, current is my null, we're going to come out of our while loop. What does that mean? Add to the end of the list. And just as a reminder of what our situation is at this point, previous is the last node of the list, and current is equal to my null. And so at this point, what do we want to do? We really just want to take this last node, which was previous, and have it point to our new node. So previous dot next equals new, and then our new node should point to my null. And this is kind of nice because what we were doing inside our loop was previous next equals new. Well, we're still doing that, and new next equals current. Well, we're doing new next equals my null, but guess what? Current is equal to my null, so we actually could have said new dot next equals current. And so this is really not an edge case either. If we run out of nodes, we can do the exact same thing that we were doing in the middle of our loop. And so that's a warm and fuzzy point, right? That's this code seems like it's making sense in kind of the eye of the universe sort of sense, because there's harmony in our different cases. Let's see, someone said in chat you could check to see if the next node is my null before current reaches it. Yes, so before we move down the list, we could check to see if current next is my null. And then if it is, we wouldn't move down the loop, and so in that case, this would still be current and this would be previous. And then we would say current.next equals new, and new.next equals my null. And that works great too. All right, so one more thing to check. What if the list is empty? So suppose we had a case where our sentinel was pointing to my null, and we wanted to add a number. All right, what's it going to do? It's going to initialize our loop by saying previous equals 0, that's the sentinel, and it's going to set current equal to my null, because that's, you know, previous next. And our while loop is saying, well, my null is not current. Well, current is my null, so our while loop is going to exit right away, which means we're going to come down here to where we want to add to the end of the list. So, you know, we've made a new node, presumably. So what does our code do in this case? It says previous next should be new. So this will point to our new node. And then new next equals my null. And again, that's perfectly correct. If you had an empty list and you added one thing to it, the sentinel is now going to point to that new node. So you got one set of code, some initialization, iteration with an action taking place in the middle, possibly, and then an ending case if you fall off the list. And it works in all of these cases. Works for an empty list, inserting the beginning, inserting at the end, inserting in the middle. So that's good. All right, so one more time, right? The goal is to understand the list manipulations. This follows from what you want to have happen to the memory of the machine, right? So when you're going back trying to figure this out, don't be looking at this, be looking at that, right? And let this follow from that. So try to figure out from what you want to do here, why do we write these things down in code, right? But this is really the spot where you want to understand this and other data structures. Yes, you need to be able to add any integer, which therefore includes negatives. There's no special handling that has to happen with negatives, though, right? scanf doesn't treat them any differently from positives. Your comparison doesn't treat them any differently from positives, so that should not come up in your code at all. Also, if you know how to do recursion, don't do a recursive solution for this. I'm gonna post an announcement after classes today and just remind people that I want them to be working with the linked list as a linked list, right? Starting from the sentinel, following the nodes. All right, other questions? That's pretty much everything that I can say on PA1. All right, well, we got 72 seconds left. I'll let you out 72 seconds early. Keep going on PA1. Bring questions to class tomorrow. And we will start talking about where we go from here, which is implementing these linked lists inside dynamic memory. So we'll start looking at pointers tomorrow and for the rest of our lives. All right, have a good afternoon. I will see you next time.